For this session, we have Professor Soumitra SenGupta from ICS Kolkata, and apart from being a very good scientist, he is also a very good piano player. So he will take us to a musical journey through the wonderland. So Professor SenGupta, please.
So my very sincere thanks to the organizers, because this is a wonderful podium to talk about a person who not only taught me physics, but he taught me how to think about physics. I had the privilege of being a student during my undergraduate time, during my postgraduate time, and then for many more years during my research time, because I was working in the field of gravitation. And on numerous occasions, I had many discussions with him, and it is difficult to describe him in few minutes. But as you have heard from Professor Palash Boronpal, Palashda, that some glimpse on AKR. So I will just mention in 5 minutes a few experiences with him, and then I will go to the main topic of this lecture, which is dedicated to him. Firstly, let me tell you about one aspect of AKR which we experienced. It's a very different side of AKR that we, in our college days, there are many teachers in Presidency College apart from AKR. Of course, none of them could match with AKR, there is a question. But some of them were very bad teachers, but they were good human beings. They were very nice people. So for one such person, I won't name, few of us used to bunk classes regularly, and we didn't go to class. And at that time, AKR was the head of the department. So one day, AKR called 3 of us and told us that, see, that particular teacher went to AKR and expressed his pain that we are consistently remaining absent from his class. So AKR told us something which I'll never forget. He said that, see, when you go to a class with the hope that you will learn something new, you will hear some excellent teaching, that expectation is something most valuable to us. The expectation of a student from the teacher. But on the other hand, you should remember the expectation of a teacher from the students. That when a teacher who is otherwise sincere, who is very honest about his teaching, but cannot teach well for many reasons, when he goes to class, he also has a lot of expectation that today I will try to explain something and student will listen with joy and happiness. So do you think that just as a teacher should not disappoint a student, should a student disappoint a teacher? And here the question is not about the quality of teaching, it's a question about the ethics of life, that how we handle each other in an academic institution. I think this was remarkable that this statement came from a person who himself was such a great teacher, but he was so sensitive about the pain of one of his colleagues. So, but after hearing this, of course, the whole atmosphere became very heavy, and we are remaining silent because we knew that what he was saying is right. So we were quiet. Then to make it slightly lighter, he said that now, of course, one day I will hear that you are saying that, okay, now we will not attend AKR's class because after all, he is no Feynman. Now we could realize that he knew his level with whom he should be compared. So that was AKR, one side. Second, I had mentioned that there was a long an interview in YouTube, which some of us went to Eckert's house and we got this interview from him. And there were many other personal conversations with him when I used to go to his house and we discussed many physics. So one day he made two comments I would like to share with you. There are numerous cases, but I just mentioned two comments. One is that he told me that, see, you have to understand one thing, that I am not a very brilliant person. But I know that I have one quality. The quality that I am courageous. Because I could question a theory which was proposed none other than Einstein. So if you want to do good physics, have a lot of courage. I think this is one of the greatest lessons that I got. You have to have courage to do something good. There is no alternative. Whether you are brilliant or not, that comes later. You have to have courage. Second, when I asked him that after your equation, when Hawking and Penrose went forward with that and did their famous singularity theorem, what were you doing at that time? Because you could have done that also. Then he was teaching in an undergraduate college with no facilities, nothing, absolutely nothing. He could have given a lot of excuses, and which are some valid reasons. Instead, he told me that, see, the mathematical techniques that Hawking and Penrose they used, I couldn't follow that. And so I couldn't cope with them. Now this, I was so overwhelmed by this, because this is the kind of honesty that a scientist should have. He never tried to pretend. So these are some of the hallmark of great minds. And there are endless stories, so I wish that I could share. Paulazza has already done, but I have shortage of time. So I will conclude by giving you one case where I found Eckert as a teacher. There are so many cases I can remember right now, so many things are crowding my mind, but I will give you one example. Because why I have chosen this example, because this was our first class with Eckert. And the first class he took was electrostatics and magnetostatics. That course he took our first class and in our undergraduate time, bachelor's BSc. And he entered the class and he explained Coulomb's law. Now, why am I mentioning this? It is not that you do not know this, all of you know this, but the way he introduced to the students who have just completed their school, you will get the one example that where he was very different from others. He said that, you know, the force between two charges. So suppose this is the force between two charges, Q1, sorry, where is that? Yeah. So this is one charge, and he said, suppose the charge is a point, it's a point charge without any dimension, it's just a point. And this is another point charge. He said, all of you know that Coulomb's law is given by this. So this is r vector by r cube. That's the r magnitude will cancel. So it will be 1 by r square force between two charges with r unit vector directed along this. So he said, suppose I do not know Coulomb's law. I have given you 2 point charges. What can you say? So he said that, see, the force being a vector, it will have a direction. In which direction the force should be? So he said, see, the force, if suppose the force given by capital Q, 1 point on this small q, if the force is in this direction, suppose this direction, then you can legitimately ask why the force is not this direction. If you say the force is in this direction, you can ask why the force is not downward. Why? Because space, the vacuum is symmetric. It is isotropic in all directions. So if the force is in this direction, then this breaks the isotropy of space. So which is the direction which is unique is the line joining them. this direction is unique. Otherwise, for every direction, you can put a counter argument that why not this one. So we say the force has to be along the line joining them. And so why? Because the space is isotropic. And then he said, if you now take these two charges and this is not work, yeah, and then you shift to some other point, then the force should be same because the space is also homogeneous. And therefore, where you have kept it doesn't matter. So first you conclude without knowing anything, the force between two charges has to be along the line joining them. It can be attractive, it can be repulsive. But it has to be either this way, repulsive, this way, attractive. And then he said that there has to be some quantities on which the force depends and the properties that I define what is called electric charge. And that should be same if I exchange them because space has that symmetry. So if you take their product, there is one choice when this symmetry is preserved. And then so what I'm trying to say, then he went on, I wish I could say, but then he said about Gauss's law, about the inverse squared nature of force. So in first class, I realized that a person who, to the students coming from school, talk about the importance of isotropy and homogeneity of space. He said, suppose if I keep a medium somewhere here, then you have broken the isotropy of space because you have chosen the upper side with a medium. But then the force will not be along the line because you have broken the symmetry. So in that class, we have got completely awestruck that, I mean, how a property of the background space can tell you about this. So I'm giving you this example. Every classes were like this, full of insights, full of concepts. So it is extremely difficult to find such teachers. And of course, it is, as a researcher, his contribution, as you understand, the recent Nobel Prize was kind of inspired by his work. So I thank the organizer for organizing the meeting to this in memory of this great person. And I consider it's a privilege that I had for so many years, I had such close contact with him. And I wish I could tell you more about him, but due to shortage of time, I now move over to the main topic of today's discussion, a journey to the wonderland of hidden dimensions. Now, this is an area of research which is very frontier research. My objective is to give you some glimpse and idea of this. And the objective is not that you will understand everything of this, but objective is to trigger some ideas that the people are thinking in the modern day research. And this area is, of course, related to the research that AKR was doing. So this is one of my research area. And regarding the absorption of communication, as Polazar told you about the comment of Gerosh, the absorption percentage will tell you about the success. There is a counter statement, but not opposite statement, by Richard Feynman, who said that when I teach in a class or when I communicate in a class, I ensure that everybody understands a part of it, but nobody understands whole of it. So it is important that the absorption coefficient should not be 1. Okay, so I'm neither Gerosh or Feynman, so it will be somewhere in between. So I will try to explain you this beautiful area of research. We all know that suppose a set of ants are going along a line, and they can only see the path they are moving, and they say, oh, it's a beautiful world of one dimension. And this is absolutely legitimate statement. But now suppose a set of ants, they are moving on the surface. They cannot move up. They cannot see upside. They will say this universe is two-dimensional. They are also right. And then we, standing in this room, we are saying we are in a three-dimensional room because we can see the another direction. So the world, now we say it is three-dimensional. We will tell these ants that you cannot see the one direction. They told we will tell this ant that you cannot see the other to the second direction, and so on and so forth. So then what is the dimension of this universe? So we will all say that we are human beings, that it is 3. We all are saying 3. But the question is, how many space dimensions are there? And you will say 3. And how do you know this? That is what we see. And we all agree. But you will agree also, but there are so many things which you cannot see. And do you say they don't exist? Have you ever seen an electron by your eyes? Have you ever seen an atom with your eyes? So you cannot say that it doesn't exist. So I cannot see is not a good enough answer. So you understand, maybe there are more space dimensions which are invisible. Because whoever created this universe and whatever way it has been created, the number 3 is not a magic number. Why 3? Why not 4? Why not 5? Why not 6? Is it that our brain can only perceive 3? There are more dimensions. Possible? You all agree? So then the question is that why we are then thinking about this unnecessarily? The life is fine with 3. Why are we thinking about more? The reason is, suppose they exist, suppose, can they have some indirect influences on our visible three-dimensional universe? Suppose they exist. In this room, there are more dimensions. But also, if I say that yes, they are invisible, but their influence is there, their footprints are there in this room, those dimensions, then why are they invisible? That's a very legitimate question. You have to explain that why are they invisible. So let us answer these questions. First, we answer why are they invisible. One possible reason is they are very small, and so small that cannot be detected even by the most powerful microscopic resolution, which is roughly this, which is done by the Large Hadron Collider. So what we do, we throw suppose some light. Now more is the energy of the light, that is more is the frequency, because E equal to h nu, all of you know. That is smaller is the wavelength, because frequency and wavelength are inversely related. Then we can go inside. For this reason, light cannot penetrate your body, but X-ray can, because it's a smaller wavelength and therefore high energy. So in this machine, we can generate a very high energy beam which can resolve roughly up to this resolution. But suppose that dimension is smaller than this. That's very strange, because the dimension we are used to see from -infinity to +infinity. Then what do we exactly mean by small dimension? I will explain. But for suppose you accept that there can be small tiny dimensions, then they are invisible. Now we can explain the invisibility. Consider, suppose you start with a 2-dimension, this length and this is breadth. Suppose this direction is our, for simplicity you assume this is our XYZ, all symbolically I have drawn along this. And this is that extra direction apart from XYZ. Now suppose I give you an example. Suppose at the time of the creation of the universe, they were at 3 and 1, 4. Now after some time, as the universe expanded, one dimension started getting curled up. And it became like this. So see this side, these two sides are getting curled up and forming like this, and eventually becomes a cylinder. You agree that this paper can roll into a cylinder. And then as time passes, the radius of this cylinder becomes smaller and smaller. And this radius becomes so small that it is less than that 10⁻⁻18 meter, the smallest resolution. then what happens? You will not see that, you will only see this direction. You will only see this direction, x, y, z, and you will say we are living in only along x, y, z, the other direction has disappeared. But it is there in this room, it is there everywhere, that small dimension. This process is called compactification. Now, you may say, okay, is it the only way for invisibility? So as I said, suppose R is beyond the resolution of our most powerful microscope, so it becomes invisible, as I said. So one space dimension has disappeared because of this curling up. Suppose it happens with cosmological evolution. I give you one example. That's a possibility. There can be another reason of invisibility, that extra dimension is not small, they are pretty large, but still you cannot see them. How? Why? Extra dimensions are large, but light, sorry, this is also not working, I think the previous one was better. Extra dimensions are large, but light or other particles cannot enter there, and only gravitation can enter there, which being the weakest interaction cannot detect size smaller than this. Now what do I mean by this? When I was saying the sending electromagnetic wave, X-ray or gamma ray, you can go inside, see very small size. Gravitational field is very weak. You know that gravity is a very weak force, and therefore it cannot have that energy to go into that smallness. So suppose you are thinking like this, that all the light particle, that is the photons, they are confined on this wall, and only gravity can enter in this extra direction, but that everything otherwise suppose stuck into that wall. Then somebody will not be able to see this extra direction because there is nothing, no probe. Suppose I make this room dark, this entire inside, only the wall is there, with lighted wall. You will see that our room is two-dimensional, this wall. This third dimension has become invisible because light cannot enter, no particle can enter in the direction. This is large. So another reason of invisibility is that standard model particle means our known particles, they stuck on this surface, which is called a three-dimensional brane, that is membrane, and only gravity propagates, but gravity cannot resolve very small distance, and therefore even the extra dimension is pretty large, maybe few microns, but then still you will not be, or less than few microns, you will not be able to detect this extra direction because of the confinement of the particles on the surface. So see how the stretch of imagination can go from to understand the existence of extra space. But how to test existence of extra dimension? There can be two ways. One very direct, other is indirect. Direct is that you increase energy, try to increase your energy and try to go inside the extra dimension. As I said, that by increasing energy you go inside your body by X-ray, increase the energy, and energy has to be so large that it can probe inside that smallness, and then you can see that. So one is direct, go inside using high energy. The other is not direct, not using high energy, but see the prints of them. Suppose there is something in this dimension which you cannot see, but by some way I make a projection or image of this object. I can see the image of this. I am here, I am confined here, I cannot see this, but I see its image being projected here. I will explain you what I mean by this. So these are the two ways to understand. So these are the most modern things that you are learning, that how to understand the existence of extra dimension, but they are not directly visible. These are very mathematical. I have tried to avoid mathematics as much as possible, apart from a little bit. Now the question is force in extra dimension. As everybody said, today we heard about the problem in understanding force, but however, suppose we assume that we know about force. Presence of extra dimension modifies the force law. Coulomb's law and Newton's laws of motion, gravitation exhibit, all of you know, inverse square law, that is 1 by r square, in our universe with 3 space dimensions. All of you know this. And this has tested up to, this inverse square nature has been tested up to 10 to the power minus 18 meter without any deviation. So you may say that if light can enter into the extra dimension, the size of the extra dimension has to be smaller than this. No modification found. And all of you know Newton's force of gravitation, which is very weak force. So this has been tested only up to few microns. This is not exactly right, but then F is this force. So we can allow the extra dimension to exist where only gravity enters. Then the extra dimension can be reasonably large, because gravity cannot probe such beyond smallness. Gravity is not so powerful. What happens? The gravitational force explained inverse square law, so the planetary motion, therefore there is no modification at the planetary distance level, but the modification can happen at a smaller level by for gravitation force also. This is successful in describing many natural phenomena, but have significant effects only when masses are very large. Why? Because the value of G, capital G, Newton's constant, is very, very small. This constant has such a small value that unless the masses are large, it really doesn't have effect on our daily life. Say between two bodies, two persons sitting side by side, there is force of attraction of gravity, but that's not much. But for planetary motion, it explains brilliantly. What happens with extra dimension? The new theory of gravitation, I have written this, and I can tell you this is a very simple way that if you want to preserve Gauss's law, which you have studied in your BSc classes, if there are d number of extra dimension, then this law will be gmm by r to the power 2 plus d. And that is easy to understand because in 3 dimension, a closed surface sphere is 4 by r square, right? And so when you calculate the flux, the 1 by r square and r square, they cancel, you get that. If you want to preserve that in higher dimension, in 4 space dimension, a surface is 3-dimensional. A 3-dimension, suppose in 2-dimensional plane, a closed loop is 1-dimensional, right? A circle, 2 pi r. Then in 3 dimension, a closed surface is r square. In 4 dimension, it will be r cube, 5 dimension it is r4, 1 lower. And therefore, for d extra dimension, it will be r to the power 2 plus d will be the modification of the inverse square law. And g, in that case, is the Newton's constant in higher dimension, because we have written, so suppose we are living in a higher dimensional world, and this is our new Newton's law, and capital G is the new Newton's constant. So Newton constant may not be a constant, that I will show. So what happens? Suppose we assume 1 extra dimension, then it will be 2 plus 1. So new law is gmm by r cube. Now suppose you cannot enter into the extra dimension with that energy, you are sitting at the surface of the outer rim of the extra dimension, you don't have the energy to go inside. Then 1 of the r will be replaced by capital R, which is the radius, because you are sitting in the other direction, you are sitting at the r. So 1 r is replaced by capital R, and you get back your old law gmm by r square, because now you are not being able to enter into the higher dimension, you are in your 3 dimension. In 3 dimension, you have retrieved your law gmm by r square only if you identify this g nu by r to be your old Newton's constant, because then you retrieve your old law from this, and therefore you get g nu is g old times r, and it can be shown for appropriate value of r, especially for large extra dimension, g nu can be large even though g old is small. That is, our 4-dimensional Newton's constant is small, but 5-dimensional Newton's constant is pretty large, which means gravity becomes a strong force in high dimension. So that is, suppose we see gravity is a very weak force, and 2 of you are sitting side by side happily, but suppose you are pushed into the higher dimension, then you will just crash into each other, because gravity has become strong force in the higher dimension. So this is a remarkable feature that Newton's constant actually is not a constant. It depends on the number of dimension, space dimension. Now, let me talk about a different thing for some time, and then we'll go back to the extra dimension, the main topic, because I need this discussion. That is, what was Einstein's theory? According to Newton, gravitational effect is transmitted instantly. Suppose I have this is sun, this is earth, and the force is gmm by r square. You remove this, immediately the earth changes, and this senses that the earth, sun has moved, because the r has changed. That is, the information that sun has gone here instantly felt by the earth. And this violates one of the very important principles which we will learn sometime later, called spatial relativity, that no information can travel faster than speed of light. So clearly, the Newtonian law of gravitation is in contradiction with spatial relativity. That is, no information can travel faster than speed of light. And therefore, Einstein came forward with a revolutionary concept, the connection between geometry and force, which I'll tell for a second, and then we will go back to our extra dimension. Newton thought that space-time is flat. A body travels along the shortest path, as you have heard today morning, that is a straight line in absence of force, and accelerates when there is force. That's the statement. And I mean accelerates a curved path in space-time. Now, I ask you to think about one thing, that you can say that if I release something, this is accelerating downward. But it's accelerating, but path is straight, right? Where it is curved? Remember, it is curved in space-time. I have remembered this, not in space. In space, it is straight line. But why it is curved in space-time? Because when it accelerates, the equation is x equal to ut plus half gt square. In space-time, it is not a straight line. In the space-time diagram, it is a curved line. It's a parabola, basically. So whenever there is an acceleration, that is the second derivative of x is not 0, then the path will be always curved, because the power of t has to be greater than 2 or greater than 2. And therefore, curved line means acceleration, and acceleration means force, according to Newton. So no force, straight line. In presence of force, curved line in space-time, of course. We cannot draw time axis, we cannot see time axis, but if you think about time axis. So in presence of force is a curved line. Einstein said there is no force. So sun is not attracting the earth. Sun curves the space-time around you, space-time, remember. And in a curved space-time, when you move on a curved surface, your path will be automatically curved. And seeing your path to be curved, you are thinking that there is an acceleration, and therefore there is a force. So force is an illusion. Sun is not attracting the earth. Sun has changed the geometry around it in a way that earth has no option but to travel like that. So this is indeed incredible. Such kind of, these are paradigm shift, and that replacing the concept of force to geometry. So presence of mass energy curves the space-time, the shortest distance. Now, since there is no force, it is traveling along the shortest path. Newton's first law still holds. It is traveling on the shortest path, but shortest path is now not a straight line, because the geometry has changed. And therefore, the shortest distance is now a curved line, giving the illusion of acceleration, and hence the existence of a force called gravity. So force originates from curved geometry. This is Einstein's general relativity. Now, to make it little bit, give you some sense of mathematical understanding, consider 2 point the xy in this space, and you know that d square is x square plus y square through your Pythagoras theorem, right? But Does Pythagoras theorem hold on a curved surface? So consider the surface of a sphere and draw a triangle. The answer, as I will show, that is no. In 3 dimension, of course, it is x square plus the distance between the origin and that coordinate is x square plus y square plus z square. All of you know this. And therefore, I can make it like this, that in a flat surface, this is true in a flat, which is called Euclidean-like surface, there always exists a coordinate which called Cartesian coordinate, where the distance between 2 points separated infinitesimally, it is right, stopped working altogether. I mean, yeah. So the distance between 2 points separated by infinitesimal distance is given by this. All of you know, if you call this point 1, this point 2, x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square is equal to the total distance. Right. And this you learned in your Cartesian coordinate geometry, which you have learned in your school days, but this doesn't work for curved space. That geometry, when you are being taught, probably it has not been told to you that this is true only for a flat space. So what happens for a curved space, that for flat space, the distance square is 1, see the coefficient of the differentials are 1 dx square, 1 dy square, 1 dz square. What happens for a curved space, this becomes 1 plus some function dx square plus 1 plus some function dy square plus 1 plus some function dz square. At least one of these function has to be non-zero, and that is the sign of the space being non-flat. So this is a mathematical description of a non-flat space, that there exists one coordinate where there exists no coordinate where you can write this as 1 dx square plus 1 dy square plus 1 dz square. There will be at least one coefficient where it will be 1 plus some function. These coefficients are called the metric of the space and determine whether the space is flat or curved. This is a very clear, unambiguous mathematical statement. Now, as we know that every event is described by not only 3 space, but also at what time it has happened. So actually we are living in a 4-dimensional space-time. So event has to be described by time as well as this coordinate position. So therefore, we consider this, since we are talking about for curved geometry in space-time, as I told you, we define the 4-dimensional distance as 1 plus f1 dx square, 1 plus f2 dy square, 1 plus f3 dz square. How all these things are so strange? I mean, okay, 1 plus f3 dz square, and you see that should be 1 plus f4 dt square, but it has come with a minus sign. The reason is the following, that I may try to explain you later, that if we want to preserve the condition that speed of light has to be invariant quantity, constant, irrespective of the reference frame, which is the relativity says the speed of light is constant in all inertial frames, that is c, all of you know this, then that minus sign guarantees that. Now, from this metric means this quantities f1, f2, f3, f4, which measures the curvature, we construct the quantities, 2 quantities r and r, you have seen I have written, which measures the curvature of the space-time. So which means that the curvature will be equal to 0 if f1, f2, f3, f4 all are 0, the coefficients are 1, then the curvature is also equal to 0. So these quantities are constructed. And actually Einstein was looking for such a quantity. He immediately related. I have written in a very symbolic way. Actual equation looks a little more difficult, but this equation captures the meaning of Einstein's equation. One side you have the curvature, other side you have the mass or energy. So mass energy produces curvature, and this mass energy which produces curvature, see I have written mass energy curved space-time, particle now travels in a curved line, and we imagine that there is a force called gravity. Remember, this K is related to Newton's constant capital G. Yes, 10 minutes. Okay. So, okay, this cannot, it's not working. So, flat space in Cartesian coordinate and flat space in polar coordinate. This, all of you know that you learned x, y, z to r theta phi. And you will see that this coefficient are 1 and 1 because this is a flat space. And when you take this, solve Einstein's equation in for solar mass m, I find that the geometry becomes this, where see this is no longer 1 and 1, it has deviated from 1 and 1, which looks like Newtonian potential. And this Newtonian potential, you can, if m equal to 0, the space time is flat, and f equal to non-zero, the space time is curved. You can see this is no longer 1 1, the space time is curved. And now if you solve mass energy as if it has inducting the curvature and the dynamism to space and time, so consider solar mass and solve Einstein's equation to find the path of a planet. The result turns out to be an ellipse. So see, this is a remarkable achievement, that now with this, if you solve Einstein's equation, find the shortest path, it turns out to be ellipse. That is expected. Now it turns out to be something more than an ellipse. What it turns out, that the ellipse are not fixed. The ellipse after first circle, it is the next circle is this, the third revolution is this, fourth. So ellipse is a rotating ellipse, and this was experimentally observed. This is one case where the experimental data came after the theoretical prediction. So, and also Einstein showed that these are those f's, they satisfy this equation, and all of you can identify this is the wave equation which travels with speed of light. So he said that Newton instantly transmitting the information has gone. So Einstein said that movement of mass causes space-time curvature to fluctuate like the surface of an ocean. So this mass causes the curvature, but if I move the mass, the curvature will change because this distance is changing, so curvature will change, and the movement of this curvature of space and time is nothing but what is called the gravitational wave that has been detected in LIGO recently. So, and then of course what Einstein did, he applied his equation for galaxies which are cluster of stars, and showed, I am just jumping little bit here because of the time shortage, that the universe is expanding. If we go back in time, at some time the distance a is the distance between among the galaxies were 0, therefore whole universe started from a point, a huge explosion which we called Big Bang, about, though large but not infinity, finite time before the universe started from a point and exploded. So this is the evolution of the universe, and long after Big Bang, the clouds of gas and dust collapsed under their own gravitation to form stars, and it passes through various stages. Space-time around a massive star become extremely curved. So now you have seen that r equal to km, more is the density mass and more is the curvature, and therefore space-time around a massive star becomes so curved that not even light can escape from it if it comes within a distance called horizon. So I will show you a picture that curvature can be so vicious, and it is roughly shown that the mass should be of the order of this in order to that to happen. So see, this star has produced curvature, and this curvature can be so vicious that if you come to a certain distance called horizon, then even light will be sucked in, and the whole thing looks like black, and it's called black hole. So this all came from the solution of Einstein's equation. So these are some, and all paths converge to r equal to 0, that is the center of the black hole with a finite time, and description of their future stops there. That's not a good thing, that you cannot take the path and they remain incomplete, and this is called what is called singularity. You encounter the same thing when we had told you about this. If you go back in time, you hit the Big Bang and then you cannot flow further. Those are called Big Bang singularity, and this is called the black hole singularity, where everything entering the black hole ends. This was shown by Roy Choudhury, about which today we'll listen in great details, and Hawking and Penrose developed this. But now I come to the extra dimension back again. Hawking showed that black holes are not really black. Black holes can also, because of the quantum effects, so what we have been discussed only classical theory, but you may have heard about a little bit of quantum mechanics, that black hole can emit particles called Hawking particle. So they call Hawking radiation from the horizon of the black hole, and horizon is that surface where if you go in, you are gone. And therefore, if you look at the black hole, from the horizon, it is things are coming out. It looks like a hot surface, just like heat comes out from the surface, is like particles are coming out. And therefore, he showed that you can identify what is called a temperature called Hawking temperature, which is, you can immediately say that describes a kind of thermal character of space-time, and the things are coming out from there. So this is called this, and you can see that the Hawking temperature, which measures the mass of which is related to the mass of the black hole, like this. If you substitute the mass of the black hole to be the twice or thrice or 10 times the solar mass, which is required to form a black hole, as I say, to create that curvature, if you put that mass, then you are gone, because the temperature that you get is only nanokelvin. It is impossible to see, because we all know probably that we are in a thermal bath of 3 degree Kelvin, which was created at the time of Big Bang, called microwave background radiation. So in our universe, we are filled with that radiation, and the Hawking temperature is only nanokelvin. So the black hole that we see in the sky will never be, the radiation will never be visible. So we have a theoretical prediction, but hardly measurable. So what happens when I have extra dimension? Remember, I showed that the Newton's constant become very large. So the gravity becomes strong. And if gravity becomes strong, then you do not need twice the mass of the sun or 10 times the mass of the sun to form a black hole. Because in Chandrasekhar's calculation, where he showed that you need this amount of mass, which is related to 1 by g to the power 3 by 2. If g becomes large, then a small mass can form a black hole. And if capital G becomes changing in a higher dimension, so if you enter into the extra dimension, then you can see black holes with small masses. And if the black holes have small mass, then see the Hawking temperature m becomes small, the Hawking temperature becomes very large, and therefore now you can see the burst of radiation. So if we probe into the extra dimension, then we should detect Hawking radiation, because we will have tiny black holes. So as I said, that high Hawking temperature it emits. So tiny black hole should radiate due to high Hawking temperature. Can we detect this? So this is one area of research that is going on, that can we enter into the extra dimension by some high energy and create small black holes, because now the small mass can form a black hole, and therefore high Hawking temperature, which will emit bursts of radiations. Another consequence of extra dimension is that, consider two-dimensional world, suppose, and probably you know that in two-dimensional world, consider a massless particle, his energy is given by E square is equal to P square C square, and this is massless, so there is no rest mass of the particle, and we take C equal to 1, this is the energy of a massless particle. Now, if suppose one direction is circle, then what will happen? I hope that all of you have written a little bit of quantum mechanics, where the wave function of a free particle is given by e to the power I, px x by h cross plus py y. So how many of you have studied quantum theory, free particle quantum theory? I mean, not Paula's the raising hand. Anyway, I mean, this is the free particle. So this is in quantum theory. There is a system is described by what is called the probability function. Okay, and it is given by this. So I won't go, since you haven't learned it, I won't go into details of this. I just quickly summarize. Since one direction is compact, that is circle, therefore psi at xy should be equal to psi at xy plus 2 pi r, because we are rotating along that direction. And therefore, if you identify e to the power this here and e to the power pxx plus py, y is y plus 2 pi r, and equate them, you get py is some integer by r. This is a very simple one-line calculation. And if you now substitute it there in our expression of energy, you will see that what is the expression of energy, this. And now you see in one dimension, when you are not entering the extra dimension, it appears to be a massive particle with several mass 1, 2, 3, 4. They are all integers, so producing a tower of particles. They are called kk towers. So what we have learned, that if you are in higher dimension, take a massless particle, but from the observer of lower dimension, they will appear like, apart from that massless particle, a tower of particles have been created. The extra dimension creates the tower, and those tower of particles will interact our known particles. This kk particle couples to our known particles, and we may see their influence on extra space through modified decay, scattering of our known particles. We will see that expected values are changing. These are all being done in the Large Hadron Collider experiments. So can we see the modification of the value? Extra dimension has another important role to play. The important role is gravitational force which originates from space-time. You could ask the question, can electromagnetic force be a manifestation of geometry? The other force, then we will be so happy. And then we will ask whether nuclear forces can also be part of that. But first let us handle electromagnetic force. Electromagnetic force, can this also be a manifestation of space-time geometry? The answer is partially yes. Why? If you have more dimension. See the role of extra dimension. That electromagnetism, suppose apart from xyz, the extra dimension is given by the coordinate p. Suppose I call it a name coordinate p, this direction. So this is our xyz, this, and this is our extra direction p. Then what will be our 5-dimensional distance? Now apart from 3xyz, we have apart from 3xyz, we have this extra coordinate p, and since these are all quadratic in distance, there will be dp squared, dp dx, dp dy, dp dz, dp dt with appropriate coefficients for them. Now if you write with this 5-dimension Einstein's theory, do you know what happens? You get that these coefficients exactly appear as the electromagnetic vector potential, and you can get back your Maxwell's equation. That is 5-dimensional Einstein's theory is basically 4-dimensional gravity plus electricity magnetism. This theory has some problem, I am not talking about that, but interestingly, this is a great observation which was later used in string theory much later. So 5-dimensional gravitation breaks into 4-dimensional gravitation plus electricity magnetism. See the role being played by extra dimension. It is giving you the geometric description of electricity magnetism. So we find both gravitation and electromagnetism from Einstein's gravity with an extra space dimension. Now finally, at the last line, this is my last point, I mean, should be okay, just 5 more minutes. We now look back into Einstein's gravity in 3+1 dimension, that is what I discussed, and where we encountered actually a problem. The problem you may have heard, the problem is called quantum gravity. So I am becoming very ambitious to talk to you about quantum gravity, but let me try. What is quantum gravity problem? Quantum gravity problem is the following. According to quantum theory, you know that you may have heard that 2 electric charges give force on each other by lines of force. You have seen this, right? Coulomb's law or the Biot-Savart's law, etc. Electric force, magnetic force. But do you know actually what happens? According to quantum theory, the exchange of electromagnetic force is nothing but exchange of a particle called photon. So when two electrons are repelling, or electron and some proton attracting, it is no lines of force, forget about it. There is an exchange of a particle called photon. So quantum theory describes the force by exchange of some characteristic particle. So the electromagnetic force mediator, they are called force mediator, are called the photons, which you have heard. There is a similar description for gravitational force exchange, that is, this ground is attracting this. There is no gravitational field as such, there is an exchange of a particle called graviton. So you see that two electrons and this is called positron are coming and they are exchanging a photon. So these are various process, photon exchange process, electromagnetic interaction according to quantum theory. Similarly, two particles are moving, they are exchanging a graviton. And if you now calculate the probability of this process to happen, the calculation of this is called, in quantum mechanics we talk only about, in Newton's law we say this is happening. In quantum mechanics the language is what is the probability of this to happen. This is a change because of some inherent uncertainty in nature, which we will learn later. But forget about that, whether this process will happen or not, this will be decided by the quantity which is related to E squared times G. Now when E is the center of mass energy of these two particles, suppose you are and your friend is here, they are exchanging a graviton, that is exchanging gravitational force and going away. This is a gravitational exchange. The probability of this happening is proportional to this quantity. These are I have taken to be 1 in some appropriate unit. Now if E squared G is much less than 1, then this will be negligible, this process will not happen. So E squared G, if it is much less than 1, then this process will have no significance. So this implies that quantum effect is relevant at energy E of the E squared G equal to 1 means E of the order of 1 by square root of G. Now if you now substitute the value of G, you get a quantity called 10 to the power 19 GeV. GeV is the unit of energy, giga electron volt. And this energy is very famous, called Planck energy. So what is the lesson? Lesson is, if your energy is close to Planck energy, then you cannot ignore the quantum effects of gravity. You have to consider, otherwise you can forget about that. But at that energy, quantum effects of gravity is very important, you have to consider, otherwise you can ignore. But why it is a problem? The problem is, just listen to this, don't try to understand much, because this kind of graviton exchange between the two objects, the probability for this kind of process where two graviton have been exchanged, this is also has a probability, and this calculation turns out to be infinity. This is meaningless, the theory fails, breaks down. If you do something and still the probability of this happening is infinity, that means your theory is crippled. So what is the take home lesson from this? That I can ignore the effect of gravity as long as my energy is not that much. But if my energy goes to that a high level, the two particle, the quantum graviton exchange become important, then this kind of process will cripple the whole theory, and that is called quantum gravity problem. Gravity cannot be quantized, because quantum effect of gravity means that such process is happening and which gives result infinity. So we have learned that quantization and gravity has a problem because of the graviton exchange, and now also we know extra dimension makes G larger, thus quantum gravity scale. As I said, you see that MP 1 by root G, do you remember? I told you E is 1 by root G, which is called Planckian energy. G becoming large, MP can become very small. That is not 10 to the power 19. You may say that in our universe we are not encountering energy 10 to the power 19. You know that what is the energy of a large hadron collider of the beam? It is around 10 to the power 3. But if there is an extra dimension, then the same effect will be manifested. So suppose the two proton beams are running in the let's say tunnel, and then suddenly because of the high energy they enter into the extra dimension. The moment they enter into the extra dimension, they find that the Newton's constant has become large. And the moment the Newton's constant becomes large, they find the quantum gravity effect only at TeV scale. And then that may help us to resolve the problem of quantum gravity, that what is actually we are observing at that scale. So these are all hopes. We haven't seen them. But extra dimensions, it may appear that I have pushed by hand that let there be extra dimension, but a subject called string theory, which is partially successful in explaining some quantum aspect of gravity, naturally is defined in higher dimension. According to string theory, their extra dimension must exist. There is no escape. And therefore, we live in a three-dimensional subspace, our universe, and actual is full theory is 3 space and 1 time, the compact space-time. Okay. So now I am close to finish. Just to show you the last concluding slide, that because of various effects of extra dimension, which I was discussing about this radius of the extra dimension, they are called modulus. The effect of the extra dimension, they are called tidal charges. Various observations, we are trying to see their effect of extra dimension. One is called black hole shadow, which you have heard that recently the black hole, a photograph has been done, a large luminous ring around the black hole from where the last photons are coming inside is absolutely black. Black hole accretion, gravitational wave, everywhere, if there is extra dimension, the character of all these things will change. Everything will change. And we are trying to see, why you are trying to see there, because we have understood one thing, the modification should be visible where gravity is very strong. And the gravity is strong close to the surface of a black hole, where this is such a huge, massive object. In our world, we know the gravity is given by Einstein gravity. But any modification with extra dimension has to be there. We have done cosmological expansion, the expansion that we mentioned. We know you may have heard about the dark energy problem. Universe is accelerating instead of slowing down. The unknown matter from the rotation of the galaxy can be explained by the assumption of dark matters. In every cases, the presence of extra dimension can offer a solution to them. Every case you can develop some extra dimensions which actually is playing the role of dark matter, which is playing the role of dark energy. So you have understood probably that how the assumption of extra dimension in space are helping us to explain so many things. We don't know what will happen, but we have space telescopes in sky. We have the Large Hadron Collider, so experiments are being done to detect extra dimension. And our search for an unknown hidden world continues. So I hope many of you will join this research. And there should be hidden surprises in this hidden space. So there's no reason to believe that we live in a three-dimensional universe. Okay, thank you.
So thank you very much, sir. So we have time for 1 or 2 very quick questions.
Thank you, sir, for this wonderful talk.
Yeah, please.
Why there is no horizon like a black hole around Big Bang singularity? Is it a naked singularity?
Oh, no. I mean, see, the black hole singularity, you know, that black hole, there is, in the solution of Einstein's equation, there exists a horizon which protects this. But the Big Bang singularity is where, in what sense it's a singularity? So it is singularity because you go back through our present various geodesic that the universe is expanding, and if you go back in time, then your description of time stops there. Your geodesics are incomplete. So there is a singularity. So what I'm trying to say, that singularity should not always be visualized in terms of everything becoming infinite density. Probably you are thinking like that, if I'm not wrong, right? But you should better think that it's the geodesic incompleteness. And in that sense, black hole singularity is also a singularity. It may be cloaked by a horizon, But everything, suppose you go inside the horizon, never go, hopefully, but if you go, then everything inside for you is fine. There is no problem. I mean, suppose you go, I decide to go inside the horizon, and then I proceed towards the center. Within a finite time, I hit the center. Then what happens to me?
Maybe the tidal force affect the stretching and compression effect.
But the question is that there is, according to this model, if we take this, if you just take Einstein's theory, calculate the geodesic, you end up at r equal to 0. No force will stop you. See, these tidal effects, etc., they are being discussed in higher dimension. That exactly that they do that. You are absolutely correct. Right.
Thank you.
Yeah.
Sir, how it is different than saying that when we have lots and lots of parameters, we can fit anything. So how it is different situation, that adding more and more dimensions and explaining things?
Okay, so to that my answer would be, see, that firstly the question started from this, the whole thing started from this question. When I describe our laws, we define a background space-time, right? And then we bring in various models for various laws. But background space-time is inherent. So when we change the basic background, then actually you are making some kind of total paradigm shift. You are changing the basic structure. It is just putting a parameter. What you are saying is not wrong, that you are actually in the process bringing in many parameters of the extra dimension. Do you know what is really, let me kind of give help to form your question in a better way, that suppose you have extra dimension. That's a very big thing, that there is no reason it should be 3, there might be many more. My question is, is there any fundamental principle that what is that number? According to string theory, yes. They decide that number, that in a certain class of string theory it is 6 extra dimensions. Fine. Now, how the extra dimensions are curled up? The description I've given is a circle, right? They are compactified on a circle, but it may not be a circle. There can be very complicated geometries. So, is there any fundamental principle that what is that complicated geometry? If you can determine that, then it will be a great theory. But unfortunately, we have not been able to do that. For different kind of geometry, you are getting different kind of effect on our 3-dimensional universe. So if you change geometry of that extra dimension, our effect on the 3-dimensional universe changes. So in that sense, it is becoming something like adding parameters. That part I agree. But conceptually, it is something very new, that you are bringing the background space-time. That's something very new, right?
Okay. Thank you.
Hi. So the formula you presented for the Hawking radiation, in the denominator it has a gm. So
that's right, but you know that it will be m is changing by 1 by g to the power 3 by 2. Therefore, there will be g to the power half going up.
I see.
So,
Okay.
do you understand? So if g goes up, that increases the t. Good question, right? Exactly.
You can ask after that.
Okay. Thank you, sir, for such an amazing talk. I just wanted to ask this because I want to know about it. You said that just like exchange of photons, similarly the exchange of graviton.
Right.
But electromagnetic forces we know are attractive and repulsive in nature. However, gravitational forces, as we know, are only attractive.
That's right.
So how are we saying it's an exchange of gravitons?
Exchange means to a particle as if going. So when you imagine a force, what happens, whether it will be attractive and repulsive, that will your calculation will give you. But remember, in electromagnetism, there are 2 kinds of charges you have defined, right? But when you are talking about gravity, you have defined only 1 kind of masses. You have never defined a negative mass, right? Right? And therefore, when you do that calculation of graviton exchange, it only provides you an attractive force.
Thank you.
Right?
Sir, so in a slide, you have shown a force expression is proportional to 1 by r to the power d plus 2.
Right.
So my question is, if I make a d-dimensional space-time, or if I do the same geometry, so we are basically doing a modified Einstein gravity.
Right.
So then if I apply there's the weak gravity limit, can I reach that expression what you have written in the potential?
Yeah, so if you take Einstein theory, write in higher dimension, and do this, you arrive at the same result. Absolutely, you are correct. But once again, in Einstein's theory, there is a capital G sitting in the action, right, in the coefficient.
Yes.
That G will get modified the way it has been modified. Otherwise, you get the same result. Exactly, that's right.
And second question is, just think if we do another steps in these extra dimensions. So we need a proper G mu nu for the as a metric tensor for if I increase the dimensions. So in physics, we basically do a very good gauge choice for to decrease our Fourier degrees of freedom, right?
Right.
So in this case, if I get any result that
so here in fact you can do a similar analysis to determine the detailed analysis of various symmetries and the fixing of gauges. Yes, absolutely right. So what happens in the result at the end? Once again, this graviton, just like photon, is has only transverse degree of freedom with polarization. It has the same nature. That comes because of the constant deciding the degrees of freedom, right? That's what happens for electromagnetism, exactly.
Thank you, sir.
So I just wanted to add a little bit to this interesting question about why extra dimensions and parameter fitting are different. So you see, when you have an extra dimension or a model, underlying model, basically you have a limited number of parameters. Let us say 1 or 2 parameters. And based on the parameters, you have a large number of experimental results which are all correlated. Now, if you were only doing parameter fitting, they would all be different experimental results. So, we'd have a different parameter for each experiment. To give you an example from something which you are more familiar with, you think of the atomic spectra. So, you can explain fine structure by putting in spin. Now, spin, you put in one spin of the electron, then it gives you a host of data can be explained using that. On the other hand, if you were only doing parameter fitting, then for every pair of lines which were split, you would put in a different parameter. So, when you do an experiment, or you look at experiments, you look at correlations between the experimental results. Those are if you don't have those correlations, then it is indeed parameter fitting. But when you start seeing those correlations, that will tell you the underlying model, or if there are extra dimensions, or anything else. Just wanted to add to that.
Yeah, just what I would like to say that you're absolutely correct. So where it is a little bit disturbing is that the moduli values. The values of the extra dimensional quantities, the radius of the extra directions, those actually something like you are choosing in different situation and kind of trying to fit. So underlying theory is same, but those parameters, it depends on the kind of compactification that you have done.
No, that is fine. But any model, you will have a limited number of parameters.
Yeah,
but you will be explaining many experimental data.
That's right. Yeah.
So that's the point. The number of parameters you are choosing is much smaller than the number of experimental
that is
data
true.
you have.
Sure.
Which is, so that's why you will have correlations between them. Yeah. That is really what gives you a model.
Because that is the biggest objection to string theory, is that they have come up with so many vacua that all vacuas are, that's the whole point. But what you are saying is right.
That is another debate.
That is another debate, right? Yeah, sure.
Yes.
Okay, Professor Joshi.
I was just curious if you already explained, but the Large Hadron Collider, if at all, any indirect glimpses of extra dimensions? No way.
So far, no. But there are some indirect evidences in this kind of shadow and GW where we have done some work. That is, or say accretion physics, when you calculate the luminosity of the emitted accretion, that it actually if you use the Schwarzschild geometry, then there is the curve that you get, there is a kind of departure from the observed curve and the theoretical prediction. But if there is extra dimension, what happens? The metric, instead of 1 minus 2m by r, it becomes q square by r square. Now, q square by r square for Reisner-Nordstrom kind of black hole comes with only plus q square by r square. There is no question of minus q square by r square, right? But if there is an extra dimension, then the tidal effect of the extra dimension induces a negative q square by r square. So that comes from the Weyl curvature tensor. Now that minus q square by r square, if you include that term and with a minus sign, not plus like Reisner-Nordstrom, it becomes the curve fits much better with the observed luminosity data of the accretion. So one may argue that is an indirect evidence that with a modification of the background metric with a term which is coming very similar to the extra dimensional contribution of tidal charge, the accretion curve fits better.
So you mentioned black hole shadow actually.
Black hole shadow also same. You know, the structure of the black hole shadow become more closer to the observed shadow if you include that tidal charge, right, of the extra dimension.
Thank you.
Right.
Thank you.
So are there any questions? Any more questions?
Yeah.
Good afternoon, sir. Thank you for the thought-provoking talk. It was very good. Sir, my question to you is, do you believe in God?
Well, then you have to tell me what is God. I mean, before believing something, I need to know that what I am trying to believe, right? So what is your understanding of that?
My understanding of God is somebody who saves me every time I don't study for a test.
But you know, but then I must say he will be very biased because he is not saving everybody, right? I mean, so that's not a good thing to do. But but what I will say that the question, if you are asking me as a kind of personal faith, that is one thing. As a scientific question, as you know that many years before, even Galileo pointed out that a question can be a scientific question when it is falsifiable, whether there is a provision of proving it wrong. So if you say God exists, there is no experiment to show that God doesn't exist, right? And therefore, the question loses its scientific merit. So now it becomes a question on a personal faith. Now, personal faith, anybody can feel that by looking at the universe, that this is so amazing that to me this is what is called God, right? But that's a personal faith. And to you, somebody who saves you is God is fine. There is no contradiction with science. Okay.
Sir, also as a physicist or somebody who studies physics, what do you think we should believe in, the creation of the universe by God or the Big Bang theory?
There is no reason to believe that it has been done by God. There are some reasons to believe that there was a Big Bang. But of course the question may come, what was there before Big Bang? And all these questions will puzzle us forever. But that questions are there, but we still, at least there are some observational evidence in favor of Big Bang. But there is no evidence in favor of God. Right?
Okay, thank you, sir.
So, is there anyone else who want to ask anything?
Thank you for this wonderful talk. This is actually in follow-up to Professor Joshi's question. Mm-hmm. So regarding the signature of these extra dimensions on the black hole shadow image, mm-hmm. So you mentioned the RN metric. So is there any work which could be used to study the signatures, not on the charge but the spin of the black holes?
Yes, actually, if you include the spin, but then the tidal charge actually produces a minus q square by r square. So in addition, if you have spin, so now we are actually doing some work. So it's a good question that you asked, that by including speed, okay, so including the rotation, what will be the effect of the tidal charge when the black holes are spinning, and how that is going to modify not only shadow but also the QNM mode of the gravitational waves, as well as the accretion phenomena. So these are the three observations which are very popular now, you know that. Yeah. Yes.
Okay, so if there are no further questions, let us thank Professor SenGupta, and let us thank both the speakers. Let us thank both the speakers of this morning session. So thank you.